Okay, Joanne, go ahead.
Okay, I have this small thing coming up. Hold up.
That's it.
No, okay, here we go. Okay, hi everyone. I'm presenting this paper. It is called Hiera. It's a hierarchical vision transformer without the bells and whistles. And so this model was proposed by a group at Facebook Research. And I just want to kind of explore the architecture a little bit, maybe kind of understand some of their experiments. And yeah, and kind of, I guess, the big part for me, at least because I'm kind of new to the deep learning field, but understanding some of the underpinning architectures. So I wanted to begin by, I guess, discussing transformers. So transformers are a deep learning architecture that was kind of came on the scene in around 2017. And it was proposed by the Google Brain Research Group. And this transformer architecture, it's an encoder-decoder type of architecture that uses this attention mechanism. And the encoder block maps this input sequence to an internal learned representation. So essentially it would just take in some sequence of words, and then each word is mapped to some type of numerical representation. And this encoder maps the input sequence to these learned representations, where the decoder takes this representation and it generates a single output, which is fed back while being fed the previous output. So how does this embedding work? So essentially, embedding the input means we need to take these tokens, which might be in some kind of a character format, and we need to turn them into some type of numerical input that still contains the meaning and the underlying idea of what the token represents with respect to the other tokens. So we need to encode this and pass this into the transformer. So some embedding techniques are like word to embed. And essentially the input is a word and the output is a numerically encoded vector. And these types of word embeddings work with shallow neural network. So another part of the transformer architecture is doing this positional encoding. So the tokens that are input into the transformer, they have a sequence, an order in which they appear. And so the order of the tokens matters because, for example, if we had a sentence that was saying, I eat pizza, the order matters. So if I were to have these tokens output in an incorrect order, the meaning of the sentence would not be preserved. So we have to use some type of an embedding technique that preserves the order of the tokens. And one way that this could be done and is done is kind of embedding the position of each token on different cosine or sine waves, and depending on the position of the token in the sequence. And so these values, numerical values, can be combined with the word embeddings and use. Oh, yeah.
I just want to talk about this one kind of like briefly.
This one?
Yeah. I will, basically I find this to be like one of the least intuitive things. I mean, it makes sense that you just add like a small amount of information in order to like establish sequence, but the periodicity of the sine wave seems kind of arbitrary to some extent. It's like, I imagine they probably had to find the best period with like a hyperparameter, but like the sine waves makes sense in terms of like linear sequences, but when you move into images, this like, it's almost like you would need two periods to kind of establish like the horizontal and the vertical rows, and then like, and then like MRI, you need like a third type of dimension in order to establish positional encoding. And I feel like like if you're working with meshes and you have like a spherical typology, then you could have like a spherical type of positional encoding.
Okay.
And I think that this is
It's not surprising what people could do for Hiera.
I was gonna say, it's really the Fourier analysis.
No, but the reason why they're using the sinusoidal positioning encoding is because they want to build a matrix where you have similar tokens together, so that you don't have to go far to look for that. That's why this encoding, the position encoding by using the sinusoidal.
Yeah, I mean,
is very
to some
important.
extent, it makes sense, but there's like gonna be, I'm just basically saying, what I'm trying to say is that like, your choice of the positional encoding will like matter in terms of what you consider like relevant information, like unique information, like, I don't know.
I think about it different. I think about it, and we need harsh here, for dualities, but if you look at, all the dual spaces, frequency space, real space, inverted matrix, full matrix, it's all, usually whatever is sparse in one domain is dense in another domain, whatever, and vice versa. It's like, think of anything, like there's two work, matrix inversion and Fourier transform and any other transforms. Our neural networks are like holistic machines. They don't do algebra. They don't see like individual points. They need it in the space where everything is smeared. So instead of giving them frequency number one as a number or like one hot encoding, you're giving them the same information but in the dual space, in the beta space. So frequency space would be just one. Okay, here's that frequency or this order. They don't see a number like a single one. They don't perceive that. So you could have done just like, okay, to this embedding, add number one as an extra component. To this one, add number two as an extra. This will get unnoticed because that's not how the mechanism works. So that's all. We're getting continuous.
Alex pointed out in the chat as well, I just wanted to bring it up, that positional encodings are being learned right now as well.
Okay, let's see.
You can learn it, but you don't have to.
Well, the interesting thing about it, I guess, like if you took it away completely, it almost turns like you have like, it's like a bag of words that are classified, just like like pixels are all considered the same.
Oh, the transformer is a bag of words kind of classifier. It mixes everything with everything. Yes, so to avoid that, we add.
Not the transformer, the retention mechanism and stuff like that, right?
Yeah, the self-attention does that. Yeah. Self-attention adds everything, and once you add everything, come to the next, come to Pavel's talk. Once you add everything, that's it, you lost that information. There is no.
Well, no,
time.
that's the thing, that's why this sinusoidal position encoding is important, because you know, even though you're not losing all the information, because all the relevant information is at one place. So, like, let's say if I have, what example should I give? Okay, let's say about this meeting itself, like we are all listening to this presentation. And again, if I say something which is relevant to listening, so all the parts which are related to listening will be just relevant to just one. It will be coming in just one embedding. So that you're not losing it.
No, relevant, no, you are, you're losing the sequence totally because you're adding, the addition is commutative, so you can add in any order and get the same result. There's no way for you to say what you have added, but we have skip connections, so we keep adding the positional encoding every time, back. So every layer we remix, add the positional encoded image back to it, so the positional, all of the layers are being told, hey, by the way, this is still first, this is still second. So like with but there are two questions here. Why to encode position? And another is why to encode position in this weird way? And if you don't like Fourier, that is interpretable, to me at least, then Alex offered a solution, like, we will get something completely uninterpretable, learnable things, and then we'll figure out.
Just because they're using sine waves, like, can you give me like a strong explanation of how that implies Fourier? I mean, I know Fourier analysis involves like having a basis function of sinusoidal components, but like, other than that, what is, how do they relate to Fourier?
Like you can say, okay, you can order those sinusoids on the top by frequencies. And a frequency is just a digit and like kind of an integer, single frequency. So you can count that 1, 2, 3, 4. But 1, 2, 3, 4 is what we want to say in the sequence. We want to convey the model. This is first, this is
Yeah, of
second,
course.
this is third. But the model will not see that. The model will see continuous representation.
So you're moving in time, right? Before you're moving from time to frequency, now you're moving from sequential order. to
Yeah, from frequency to time, so.
The analog, yeah.
So are they adding more than one sinusoid or just one?
Just one.
Okay. I would think that would.
They're doing a mix and they're building their own bases,
But it's a mix of sinusoids.
but it's a
Yeah,
mix of sinusoids.
Which is what.
So if there's a mix, it makes this a stronger argument for a relationship. The Fourier.
Either way, yeah. But yes.
We held you up for long enough, Joanne.
So, to me, it's the weirdest thing about transformers, because it seems kind of arbitrary, like.
Well, see, actually, they're gonna go on to say you can get rid of a lot of this, positional encoding, and it doesn't affect the results that much. So that's, but
I
I.
can
did
get
want
rid
to-
of transformer blasphemy to say, but yeah.
Yeah, I did want to try to, I guess.
No, go ahead. You're here to see the conversation and your success.
Yeah.
Okay, so yes, transformers use this positional encoding to get these numerical values to put alongside the word embeddings. And then they use this attention concept, which is a measure of a token similarity to other tokens. And they use like a linear network to just compute these key value and query vectors. Which they then use, they combine to find the score of a word, and then to get the probability of the next word, they just use they take the softmax of these computed scores. So, the output of the transformer is the word that has the highest probability of occurring, next. And the transformer just keeps, outputting these words in a sequence until it reaches the end of like an end of the sequence token. So, people wanted to try to extend this, language transformer model to, working on images. So, how it works is we would take in an image and we would just split the image into fixed size patches. And each one of these patches can, be linearly embedded into some kind of a numerical representation that can be fed into a transformer encoder. And so after that, it also adds this positional embeddings to these image tokens. And the transformer architecture just predicts what the image might represent. That's one use of the vision transformer. And I also wanted to, I guess, discuss a little bit about autoencoders. So the purpose of an autoencoder is to encode or reconstruct the input image or sequence of tokens while being constrained to encode the input into a lower dimensional space at every step until we reach this bottleneck in the middle, which is reducing the dimension of the data, but it's creating this efficiently packed, compressed version of the input data. And then at the decoding step, they're trying to reconstruct the input again, using it's enforced by the L2 loss, between the input and the output. So taking a look at the masked autoencoder, how it works is they'll take an input image and they'll divide it into these non-overlapping patches. And they'll just simply remove a portion of the image by just masking out these tokens and only putting the unmasked tokens into a transformer encoder block. But the key here is that the positional embeddings are still present on these non-masked tokens. So then after the encoder step, we get some kind of a numerical representation and learned internal representation of these tokens that were not masked while they still have the positional representation. But at the decoder step, we bring back the masked tokens And the transformer decoder tries to reconstruct the missing pixels. So that's what the masked autoencoder is attempting to do. And some advantages of this masked autoencoder is if you can utilize it properly, basically you don't have to even train on an entire image. You can only train, basically on a subset of the original image, which is sparse, and you can also play with the amount of tokens that you train this masked autoencoder on. But so these vision transformers seem pretty nice, but they have some limitations that were attempted to be addressed by some different like architectures that came out and combined a bunch of different techniques. So one example of these like a transformer that's doing more things in order to overcome some issues with like vision tasks is this swing transformer, and there's some other variants of these types of transformers that try to preserve like local information about parts of an image. Because for, let's say, a computer vision task where we wanted to see maybe we wanted to see if there are people, for example, in this image here with this hot air balloon. Well, for large size tokens, that might not work as well. So typically the masked autoencoder or basically the vision transformer tokens are 16 by 16. They will patch the image into 16 by 16 tokens, but sometimes the tokens are basically too large to capture small local variations in the image, which makes these types of vision tasks harder. So the swing transformer basically starts with really small token sizes, and then at each one of these layers, which is a transformer block, they use larger token sizes, and they also use like these different size windows that are shifted. And they performed very well, but the Hiera authors in this paper are pointing out that a lot of this bulk is really slow, and it also makes things more complicated and maybe makes things not necessarily as efficient. So this Hiera transformer is wanting to use the masked autoencoder as a way to learn these local representations.
Can I ask something? Maybe you or Alex or both of you know. So you take the patch, and then whatever the encoder decoder outputs, you just treat it as a new patch in the generated image, just like value by value.
Yeah, I think so. I think that's how it works. Maybe Alex would have a comment, but basically from my understanding, it learns, it will try to do some kind of like interpolation to just reconstruct the pixels that were not there in the mask. Okay. So that's my
So the output patch or the output embedding, it outputs a linear or a bag of embeddings, right? Essentially with. So I've like two questions. One is, are they using two-dimensional embeddings, positional embeddings, or are they using one-dimensional positional embeddings? Like there is like how do they order those things on a grid or with respect to the positional embeddings that they're using?
So the way that
I can answer question. So basically, what you do is you take image and you're patchifying it, and then you add learnable embedding. Once you did that, you have this embedding that is ordered like basically by. So from 2D space, you're making it like 1D, add learnable positional embedding. Then to mask the tokens, you apply shuffle, like you're shuffling the tokens, and you just take the first, for example, 25% of tokens, if you're masking it 75. And then you're passing this 25% tokens to encoder. But it's on a standard masked autoencoder. So I'm not sure with Hiera how they did this pooling. Maybe it's the same way. But in masked autoencoder, it's like this. And then once you got embedding from your encoder, you can have this like random tokens that you're adding to the missing tokens. And then based on this, you can reconstruct the regional image. In some other papers, instead of random token, you can put class token. So I think in my masked autoencoder original ones, they don't use class token. That is learnable additional token to the input image tokens. And you kind of you can use this class token as a initial like initial kind of embedding for the masked tokens to reconstruct. But for Hiera, I'm not sure how they do pooling with like token. So I
Yeah,
think
I have to get into that a little bit more, but, so, and then, from what I can tell, it says, like with this model that they're trying to work with, it's like this, just a regular vision transformer. And how that one works is they swap the absolute position embeddings for more powerful relative ones, added to attention, in each block. So, but they just said, instead, we opt to start our study here by undoing this change using absolute position embeddings instead. So they showed that the relative position embeddings are not necessary when training with MAE. And then they said the absolute position embeddings are much faster. I'm a little bit confused about what absolute position embedding is, but, essentially, what they tried to do here with this architecture, they used the simplified version of a previous work, that they constructed, which was this MVIT V2. And they trained it using this masked autoencoder. And so they use a few different things to get around some common issues that, are present when you're trying to train these hierarchical transformers on a masked autoencoder. And so they said to add spatial bias, they opt to teach the model the spatial bias by using the strong pretext task like MAE. So, and the architecture just consists entirely of standard vision transformer blocks. And so for the efficiency, they added local attention within the mask units, which will explain what a mask unit is next. Those are for the first two stages, and then global attention for the rest. So I think like when the blocks are getting smaller, they're doing some kind of a max pooling operation to kind of downsample the information. But yes, okay, so these are some of the issues that are present for trying to train hierarchical vision transformers using a mass autoencoder. Pretty much like the mass autoencoder pre-training is not compatible with some of these multi-stage models like SWIN or other models that use convolutions, because the mass autoencoder deletes these masked tokens. So it can break this 2D grid, which causes errors for hierarchical models. But then, so there's been some other like attempts at getting this to work. So one attempt at trying to get a workaround for training the model using MAE is this thing called mask feed. So they tried to just basically perform the convolution over the mask token. They'll actually put information like indicating that it's a mask pixel, but they'll just convolve that, which is these authors are arguing it's kind of a wasteful use of the resources, and it slows down training significantly. But then another approach to try to address this issue with pre-training on May is so like processing each one of these tokens separately with padding. But another thing that they're saying is just kind of slows it down a lot. Even though it is sparse, it doesn't enforce the sparsity because you don't, for like this potential solution D baseline, they wouldn't process the mask tokens, but they would just go through and process the unmasked tokens with padding. But it still has the padding, which is still causing an overhead. But Hiera says that they just want to set the kernel size equal to the stride. so that it's sparse and there's no overhead. So so pretty much for efficiency, MAE is sparse, MAE is sparse. It deletes, meaning it deletes what it masks. So keeping the mask tokens fixes some issues with other models, but essentially it really slows things down. But they introduced a trick that treats the mask units as separate entities for cons, solving the issue, but requiring undesirable padding. In Hiera, we sidestep the problem entirely by changing the architecture so that the kernels can't overlap between mask units. So then they use this concept, which is called a mask unit, and then they perform attention only on these mask units. So essentially, each token can have these smaller tokens inside of it. But they're calling the big token that contains the smaller tokens, they're calling that a mask unit. And within each one of these mask units, they're treating these smaller divisions as a token. And they perform local attention within the mask units instead of the global attention with the full version of the K value. Because I think when typical vision transformers do these attention computations, they run it on, I think, the entire image. But they are trying to extract local features from these smaller mask tokens by doing this local attention. So essentially, they'll just treat these, they'll compute the Q values from these small mask units, and then they'll perform this attention using this smaller subsection as well. So the mask unit attention performs local attention within individual mask units, no matter the number of tokens in the unit. So pretty much there's another approach to computing attention, which is this window attention that performs local attention within a fixed size window, but doing so would potentially overlap with the deleted tokens when they're training with the MAE. But in contrast, this mask unit attention that they introduced in this paper performs local attention within the individual mask units, no matter their size. So like a mask unit might be larger if they put more of these smaller tokens inside of it. So they did a lot of different experiments with this model. Some of them that they did was like image recognition and action recognition on some different data sets. So they wanted to do some experiments on video and images. But typically these vision transformers, they struggle on high resolution data sets because of, because of the resolution of the images and small local differences that might be overlooked with the tokens. But then another thing is too, with this global pooling operation, it tends to be slower on videos because of the number of frames in a video. But then they also tried to do image and video reconstruction. And they wanted to do some transfer learning where they would train the model on one data set and then try to do action detection on a separate data set. And then they wanted to try doing the image segmentation and detection on the COCO data set. But before we kind of show, I guess, the results, they constructed a variety of different variations of this model by just changing the number of channels, the number of vision transformer blocks and attention heads, and the number of parameters. I think the number of parameters is like how sophisticated the encoder is. And then they wanted to test, they did this to compare with some of the previous work that they did. So I think they constructed these models to kind of compare with some of their previous other work with vision transformers. So the training time for this model was significantly faster because it was trained with this MAE, mass autoencoder, and compared to the other variant, which is mask feet, it's a lot faster. And then with the regular vision transformer, which has all the bells and whistles, the hierarchical vision transformer. It's the training time is much faster. Since this model doesn't have since it is a hierarchical vision transformer, but it doesn't have the anything like convolutions. It gets rid of the global attention mechanism, and also this model for pre-training was benefiting from the sparsity that comes from the mass autoencoder. So they also kind of tested different settings with this mass autoencoder. Some different settings that you can play with is like, for example, the mask ratio, how many tokens that you would mask out. And so they're saying like for example, the high masking ratios was leading to good performance, with video benefiting from higher masking than the image modality, for example. And they also, I think, played with the decoder depth for the mass autoencoder, and that the deeper decoder depth works better for video. And so this is just some of the statistics also about reconstructing the images and videos. But yes, okay. And so this is some of the settings that they were taking away from the typical hierarchical vision transformer. So, and they wanted to see what were the impacts on the accuracy. So for example, they replaced this relative position embeddings with absolute position embeddings. Yeah, and they're still having, it looks like better accuracy than the baseline hierarchical vision transformer. And they replaced the convolutions with max pooling. They deleted the stride 1 max pools. They set the kernel size equal to the stride, and they deleted the Q attention residual. And yeah, so these are some of the different settings that they changed. And this is some of the results on the video data. So they used this kinetics data set, which is a series of videos of people performing different actions, and this other SSV2 video data set. And I think they were doing video classification on these. So they tested this Hiera L model and a few of the other different types of models. And this is some of the results from their so where they would train the model on one data set and then test it on a completely different data set to see how it performed. So they did this with this AVA data set, and they tested it on a variety of models. And so this is where they tried to do, I think they wanted to compute the bounding box coordinates with this model and perform image segmentation. So they used this RCNN, they fine-tuned it with different pre-trained backbones on the COCO data set. They performed segmentation and computed a bounding box for object detection. And so they used this specific recipe for doing this using visual transformers, was outlined in another study. And they incorporated the multi-scale features from Hiera with the feature pyramid network.
Did they give an estimate table somewhere of the GPU hours spent doing all of that? This is just impressive and amazing, but I'm just like,
It's Facebook.
I'd like to see how realistic it is, yeah, for anyone.
Cannot compete. They have hundreds of people that run this.
But this is all automatable. It's just like, oh, run all the tests.
They have.
If you have, yeah, if you have unlimited compute resources, then of course you can do that. And it's kind of a nice engineering feat, but I think the paper shouldn't be judged by it because like, who can do it? It's like, who else?
Google, yeah, that's what made me mad about the NERM stuff, is we did do it, but not to the scale, of course, because we can't.
Oh, yeah,
We
but
just don't have the
still,
resources.
I mean, it's enough scale, yeah.
So it's impressive, but
Yeah, it is impressive, but then at first I was like, wow, this is really cool. And then I was like, wait a second, it's just unrealistic. Yeah.
Yeah, I guess.
I just say from experience, like to train master encoder for videos, like if you use vision transformer large, you might need like at least 8 nodes with 8 GPUs, so it's like 64 at least, or 128, depends on size. But video was like really pain to train. I think for images like ImageNet, comfortable setup is like at least 2 nodes with 8 GPUs, 840 gigabytes. But like video takes maybe 4 or 8 times more than images. So if you take internship for video models, don't take it. It's a pain.
But in their paper, they did mention that they're using, I guess, in their appendix, they use the NVIDIA A140 GPU for their task. For benchmark, to benchmark speed for all of these things, and they are processed. So I guess that's doable.
But yeah, so basically what they did, they constructed a simple hierarchical vision transformer by just taking one of the existing hierarchical transformers and removing a lot of the float. And then they supplied this model, the spatial bias through MAE training, math autoencoder, and the resulting architecture performed better than the existing models on recognition tasks and other vision tasks. But I guess a drawback would be too, like you just have to have a lot more resources to be able to get these types of results in transformers. But yeah, so any questions?
So the simple part is, yeah, lots of questions. Yeah, but we can go around.
We can definitely, like, some of these experiments we can do, it's just like the scale of what they do, and the amount, like, it's just not, for most deadlines, not doable. But yeah,
Well, if you don't start the year ahead, but yeah.
yeah.
So the only trick here is pooling.
Well, let's
Like,
see.
what's the main trick? Is there?
Yeah, can you go back to that list of where they like simplify the model, like step by step? That was a pretty cool figure. Like that's like the definition of the ablation, like, cool.
Yeah, so they have a series of things that they did. They kind of explained it in detail in the paper, but yeah, the main things were like removing the convolution, which slowed stuff down a lot, and then using these mask token units to like change the way that they computed the attention for the features.
Yeah, I mean, removing the attention residue is very nice because not a lot of people do that. And that actually, in any attention mechanism or any transformer model, that is the most overhead that you will find. So most of the computation power will be just for storing those residues.
So that and the stride are the biggest performance gain here. So we delete the stride, max pooling, and they almost triple performance, and then go by another 100 or so seconds, or images per second. Not the accuracy benefits after.
So, but the images per second drops at B, right? Replace columns with max poles. So there is kind of a local minimum that they still kept going and
Right.
increased after that.
Yeah.
So what if you don't replace columns with max poles? Are you jumping to 300 images per second immediately? Like, do you need to remove columns with max poles?
Yeah, I don't know. That's a bit unclear. It's kind of a question.
Yeah, but it's very interesting and very detailed talk, Joanne. Thank you.
Yeah, thanks.
Mhm.
Good.
Any other questions while we have Alex on the call? If Joanne cannot answer them herself. Well, obviously, we want to apply this to brain imaging. Yeah, so we want to go to 3D, which will be like videos, so we need 64 GPUs, as Alex said, you know.
I think a really cool application for that project that you guys are working on as well is, I don't know if you've heard about Lisa's synthetic healing stuff that she's doing with Denise. I think they're definitely related, right?
I don't know.
So she's doing, so they have stroke data and, currently they're, synthesizing stroke data. And they're trying to, you know, predict what the healthy brain would look like from the stroke data, you know, for targeted clinical, therapy or, so I think you could use this architecture very easily for that kind of.
But I think your dilated architecture will be on par with that or beat it in terms of, you don't need to hierarchically grow. You can just use the same small batches and stuff. And we'll see. It goes on record, hopefully we don't get spooked, but we have a month. Okay, then let's check what's coming next week. Before we finish. Okay, Girish, and Pratyush, are you ready to talk on the 8th on ML Ops in the cloud and beyond? Pratyush is not even here. Pratyush, are you online? Okay, we'll get to them separately. They're not in. But yeah, everyone, we'll see you next time. Hopefully for the talk on ML operations in the cloud and otherwise. Yeah.
There's a dynamics talk today, you said, right?
Yeah, at 1 o'clock, highly recommend listening Pavel arguing with two dinosaurs of dynamical learning, Eloy and that Pavel's message is there's no dynamic in fMRI. There's no dynamics in fMRI. That's going to be good fight.